This video will cover everything you need to know about the 1922 Model 50 transformer. We will discuss the history and significance of the Model 50 and 51 transformer, talk about how audio transformers are used, look at magnetic coupling versus other coupling methods, delve into the Model 50 and 51 construction, and then physically deconstruct a Chelsea core. We will determine the gauges of windings and the length of wires used. We will produce an accurate spec sheet, perform impedance tests and gain tests, replace the bad Chelsea cores with suitable facsimiles, and wrap up with reassembling 4 variations of the Chelsea Model 50 and 51 transformer. Hi, welcome to another edition of Antique Radio Archaeology. Today I'd like to do a video on the Chelsea Model 50 transformer along with the Model 51 transformer. Now, you probably know, if you've been on my channel for a while, that I do have another video out on the Chelsea Model 50 transformer, but what that is the restoration of a transformer using a core that looks identical to this core. And the problem that I have is finding a core that looks like this core is about as hard as finding the actual core. So I just happened to have one, and I was able to do that restoration to show you how you can do that. However, I need to find another solution. I have about 16 Chelsea radios that are in need of transformers. Most of them need 2 transformers. And if you know anything about the price of transformers, you know that if I'm buying 24 Chelsea transformers at about $75 a piece, you're talking some big money to try and get these restorations done. And even if I can find cheaper versions, or I can find some that are similar, I mean, it's going to take years to come across enough transformers that look like the Chelsea Model 50 transformer in order to do these projects. So I was finally fed up and decided, you know what? What I do have available are these PT431 transformer core replacements, which are actually available through Antique Electrical Supply. So this is a possibility of using these to replace these. However, as you can see, that would not be a very pretty replacement. So I'm going to show you how I can do that. But before we get into that, what I'd like to do is talk a little bit about why this is such an important topic for me. As you know, I am trying to put together the history of the Chelsea Radio Company, and one of the important parts of this history is how it got started. And the way Chelsea Radio Company got started is they were a parts manufacturer first and foremost. And among those parts was the Model 50 and 51 transformers. Now, the difference between the Model 50 and 51 is the Model 50 is what they call a mounted version of the transformer, and the Model 51 is an unmounted version, meaning it doesn't have all the stuff here to mount it. Now, these were meant to be used on a table with the early breadboard radios, and later on they used them in a good number of their production radios. Now, the unmounted version was also used in their production radios, but both were made available for consumers to build their own radios. Now, what I'd like to do with this video is get into what was so important about the Model 50 transformer. First of all, it was an engineering feat for the Chelsea Radio Company. And what I mean by that is they were able to do something that the other companies weren't able to do. Now, you have to look at the history of transformers to understand what I'm talking about, but basically early transformers were used in telephones. And telephones were kind of low quality. The sound coming through them was low quality. But in a radio, you couldn't deal with that low quality sound. You had to have something a little bit better than the old telephone transformers. So what happened is the different radio companies were experimenting with how to make transformers a little bit higher quality. Well, Chelsea Radio put a lot of work into this, and they came up with their Model 50 transformer, which actually won a Certificate of Merit through Radio News in 1924. It also got a write-up in several newspapers back when it was introduced as being a revolutionary design in transformers. Now, what made it that was basically, if you look at the transformer curves that are created when you inject audio into them, what you'll find is as you raise the frequency, the volume level will drop. And because of that, higher frequencies get kind of toned down, and the lower frequencies are a lot higher, so it always sounded a little muffled. Well, what Chelsea Radio did is they found the right combination of wire gauges, the right number of turns for the primary versus secondary, and they came up with a design that produced this high quality that actually boosted the signal so that you really had a curve that would represent the same volume level going from a lower frequency to a higher frequency. At the time, this was definitely a breakthrough in technology. So let's go ahead and talk a little bit about what a transformer is used for. Now, in the early stages of radio, you had the crystal radio, which basically used the signal off the air to produce enough electrical energy to hear the sound in a headphone. Granted, with the advent of the tube, you can use the tube as an amplifier, which was a very good amplifier, and this would give you a little bit more amplification into the headset. But what was found was sometimes that wasn't enough, and you did kind of get low volume, especially at distant stations. And what you wanted to do also was be able to hook up a speaker to a radio, so you definitely needed some additional amplification there. Now, the correlation between a transformer and a tube as far as amplification goes is that they work together, really. And the purpose of a transformer really is to couple the stages. So in a typical radio, you have the RF stage. What you want to do is you want to amplify that signal so that you can use it with headphones and subsequently a speaker. In order to do that, you need additional stages or additional tubes. You have to have a means of taking the electrical signal from the detector stage and send it to the first stage of amplification. And that method is called coupling. And there are several different types of coupling that you can use. You can use resistive coupling, which is basically taking a tube and going straight through like a resistor into the tube. You can use a coil to do that. You can use a capacitor. You just need some means of getting from one tube to the next. And one type of coupling that can be used is called magnetic coupling, and that's where the transformer comes into play. And the reason why it's called magnetic coupling, as you may know, is because a transformer has two coils. And you have a primary, you have a secondary, and what you're doing is you're injecting a signal into the primary. It is producing a magnetic field around that coil, and as that magnetic field crosses over the coil wires of a second coil, it's inducing that signal into the other coil. It's using those magnetic lines of flux. Now, as you may or may not know, if you have a few windings on the primary and a bunch of windings on the secondary, what happens is you're amplifying the signal. In other words, those few coils transferring that signal over is going to cut across a large number of coils in the secondary, which is actually going to boost the voltage of that signal. And by doing so, it is amplifying that signal. And by amplifying the signal, you are getting it ready for that next stage of amplification, which is good. However, there are limits to the amount of amplification that you can do, because as you do that, your current is also going to decrease. So using magnetic coupling turned out to be the preferred method in early radio. That's where the Model 50 transformer came in. Chelsea started using it, and it became a very popular transformer and a very big seller for the Chelsea Radio Company for its parts division. So let's take a look at the news article that was published in 1922 on the Chelsea Model 50 transformer. The core is composed of a large number of very thin laminations of the best quality silicon steel. Its dimensions are designed with the utmost care to give the greatest value of impedance. The coil winding, radio, and dimensions are designed to give the highest amplification possible with modern type of vacuum tube, and was chosen only after much experimenting with a variety of windings and turns ratios. The coil has a square section winding, enabling the turns to be wound much closer to the core than is possible with other transformers, and thereby increasing the efficiency to a notable extent. So keeping that in mind, I did some experimentation just to see how good the quality was, and what I did find was actually true. I did find that up to 6,000 hertz, which was mentioned in one of the advertisements that I had found, that it performed very well. So let's take a look at how this particular transformer is constructed. Now, as you can see, the construction of the core starts with the primary wound around a square cardboard tube. The tube is wrapped in a layer of cloth tape and glassine paper. Now, what glassine paper is it's kind of like wax paper, but it's much thinner. And then a lead was attached to the end of the transformer wire, and they used a small gauge wire and started winding. And after they wound a complete row of windings, they covered that row of windings with another piece of glassine paper and did another row. And they did this over and over again for many, many layers. Now, after it did its initial 15 or 16 layers, they used some more cloth tape, they attached another lead, and now you have your primary winding. And then they went ahead and did the same process for the secondary, continuing that wrapping and the layers of glassine paper and windings until they came up with the amount of windings they needed for the secondary. And then, of course, they tied off that end to another lead, and they wound up having 2 leads for the primary, 2 leads for the secondary, and they were separate coils, but they were wrapped around the same core. And that is the basic construction of the Chelsea Model 5051 core. Now, mentioned in the article was also the concept of impedance. Now, where impedance is important is you have your impedance, which is your AC resistance. That's kind of a loose way of phrasing what impedance actually is, of the plate circuit in a tube. That plate circuit's going to the primary of the transformer. And if you have too low of an impedance on the output of that tube, what you're going to do is you're going to overdrive the tube. If you have too high of an impedance, you're not going to get enough signal through the transformer. So there has to be roughly specific impedance that has to be seen by that plate circuit in order to have the best efficiency for the radio. With that in mind, I'm going to go ahead and take a Chelsea Model 50/51 core, and we're going to unwind it. I want to count how many windings I have, and I want to see how many layers of windings we have. And we're going to do some computations based on that to figure out the turns ratio, which I already know through advertisements is supposed to be 3.75. We're going to verify that. And we're also going to look at the number of feet of wire used, and we're going to also look at the resistance of the different gauges of wire, as well as figure out what the gauge of that wire is. So there's a lot to be done, and I'm going to go ahead and jump right into it. This is getting interesting here because the wax paper is not coming off of here, and I think it's because I'm at the end of it. I'm at 14,397, so I'm having to pull through the wax paper. Okay, I think I found the end, and it's wrapped the opposite direction as the other one, so I'm going to reset that. Spun around. Okay, so just finished up at 3952. I don't know if that's an exact measurement because I did lose some in the process of trying to get this thing started, so I'm willing to bet it was about 4. Another 50 turns, that'd be about right. Okay, so this is what it looks like, fully disassembled. I've got a cardboard core with some wire attached to it that can be soldered onto the terminals, and that is attached to the primary coil wire. And I've discovered that it's about 290 or so turns per layer, and each layer is separated by one of these glassine partitions, which is coated in wax. And I discovered there's about 14 of those layers in the primary, and then you have some cardboard covering that, and then you start the secondary with some more, with another. Of course, you got the end of the primary tied off to some of this wire here. You've got the secondary tied off with some of that wire at the beginning of it, and then I go through 47 layers. Each one of those is about 310, somewhere around there, windings per layer. And finally, there's a little bit of cardboard covering the outer shell, and then you've got this electrical tape covering it. So that is the construction of this transformer. Now, my next step is I've taken some of the primary wire and some of the secondary wire, and I'm going to measure how many ohms per feet each one is. Now, these are different gauges. This is slightly bigger than this, and as such, you're going to have differences in resistance. Now, whatever the ohms are per foot, I'm going to be able to divide that into the total ohms per foot on this transformer here, which is actually a new old stock transformer, which I acquired a while back, and I'm going to use that as my reference transformer. So we're going to go ahead and go into those measurements and try to calculate how many feet of wire are on each winding. Okay, that's 1.4 ohms on the secondary, 1.1 on the primary. Okay, so my next step here is to figure out what the diameter of this wire is. Now, the reason I want to do that is because I need to know what the diameter is in order to figure out what gauge wire this is. And the way I'm going to do that is with a micrometer. And I'm going to take that, I'm going to use this chart here to figure out the gauge. So here's my micrometer. I already cleaned the jaws. If you know anything about micrometers, you know that's the first step. So let me go ahead and turn this on. I'm going to set it for millimeters. Zero it. Let me get that wire in there. I know you can barely, may or may not be able to see this wire. Right now it's in the center of that jaw. Okay. I'm reading 0.071 millimeters for the secondary. 0.071. 0.078 millimeters. Alright, so I just need to figure out what the gauge is. Let me see. Okay, so for the secondary 0.071 right here, it's going to be 41 gauge. And for the primary, I had 0.078, closest I got is 0.079 right there, so that's 40 gauge. Alright, now if I look at my resistance per thousand foot, for the 40 gauge I'm reading 107,920 ohms, and for the secondary at 41 gauge 1323 ohms. Now, if you remember, when I did the 1 foot measurement, I was reading 1.1 ohms on the primary, times 1,000 feet would be 1,100 ohms. And I was reading 1.4 ohms on the secondary, which would be 1,400 ohms, which, as you can see, is pretty close to that 1323. 1,100 is pretty close to that 1079. So I think, based on my resistance measurements and by my micrometer measurements, I believe I've got the gauges right. 40 and 41 gauge. We can use this now to calculate how long those wires were. So now that we've totally disassembled the transformer and kind of figured out where we are, I went ahead and took the numbers that I came up with, took a look at the research, and pretty much figured out where their frame of thought was. Now, granted, the manufacturing process is probably going to produce different results for different transformers. So based on my findings, what I discovered was, let's look at the primary first. There are 14 layers of windings. There are 285 windings per layer. There are about 4,000 total windings in the primary, and they're using a 40 gauge wire. 40 gauge wire has a resistance of 1.1 ohms per foot. Now, I know from measuring many different transformers that I'm looking at about 935 ohms of DC resistance. Based on 1.1 ohms per foot, that gives me 850 feet of wire. So that is the primary on this particular transformer. On the secondary, there are 50 layers. There's about 300 turns per layer, so that's about 15,000 total turns. They're using 41 gauge wire, which is a little bit thinner. That has a DC resistance of about 1.4 ohms per foot. That, using my 6,300 average ohms DC resistance that I'm finding on looking at several transformers, I have about 4,500 feet of wire. Now, if you do your simple math and you divide your 4,000 turns into your 15,000 turns, what you're going to find is you have a turns ratio of 3.75 to 1, which is also your amplification. So with all that, we now know what we need in order to replace this transformer. Now granted, the PT431 transformer does not match this at all, but it is within range of the impedance that I need on the plate circuit in order to use it. So no, it's not the ideal transformer, but you know what? I just cannot leave this many radios unrestored because it's going to take me a lifetime to find these transformers. So I'm going to go ahead now and I'm going to show you how I'm going to take the PT431 transformer and put it on the Chelsea laminations. So for the input impedance test, what I'm going to do is I'm hooking a 10K pot in series with the input on the primary here. And what I'm going to do is I'm taking the secondary, I've got that on a 2K load, which is this speaker, and I've got the multimeter hooked up so I can read the output. And I'm going to set this up for a 2 volt output. And then what I'm going to do is I'm going to increase the resistance until I can lower this output down to 1 volt. So I've got 2 volts, I'm going to lower it down to 1. So let's set this up for 2 volts right there. And that's about 1 volt right there. Okay, so my next step is to go ahead and put this on ohms. I'm going to see where my pot is. I'm at about 3.5K. So that's my input impedance, is 3.5K. For the secondary, what I'm going to do is I'm going to get rid of the load. I'm going to take my potentiometer here, and I'm going to be putting it across secondary here. I'm going to max this out. And I'm going to adjust this down to, okay, at maxed out, I'm reading around 2 volts. Let me get this exactly at 2 volts. So I want to, again, drop this down to half. Okay, that's about half right there. Now again, I'll switch over to ohms. And my output impedance is 4.3K. Now, a couple of things to keep in mind. This impedance test is based on 1K. If I change that to another frequency, obviously the results are going to change. Actually, as you change things around, such as loads and things like that, all these parameters will change. So I'm using 1K because it's a lab standard, and my load is about 2K on the speaker, so that's what I'm using. This is where I'm showing my impedance at 1K. But right now what I want to do is I want to check the gain real quick of this transformer. 1 volt AC, 3.73 volts output at 1K. Now what that shows me is I have a gain of about 3.7 to 1. So as you can see, my gain pretty much at 1,000 hertz. mirrors the turns ratio. Now, here's where things get interesting. As I increase the frequency, let's go to 3K. I'm going to have to come back here, readjust that for 1 volt. Now you can see my gain is actually 4.5 volts, or 4.57. So I'm seeing an increase from 1 to 4.56. Now if I go back and increase this to, let's go to 6K, increase that to 1 volt, I'm seeing 8.7 volts. So as you can see, as I increase my frequency, my gain is actually increasing on the transformer. So that was one of the selling points of this transformer, is it did show a higher gain at higher frequencies. One of the reasons why I did this is I also want to show a comparison between this transformer and this one right here. This is the PT156. Now the PT156 transformer is basically a PT431 core with the iron laminate. So the reason you need to do this with the iron in it is because without it, you just got an air core, and your number's going to be skewed all over the place. So I'm going to go ahead and do the exact same thing that I just did, only with this transformer, and we're going to see what our results are there. So let's start with the impedance test. My input impedance is 2.9K. And I'm reading 3.46 or 3.5K output impedance. Now let's see what the gain is on this one. I've got a gain of 3 on this one. So as you can see, these things are a little more compatible than they seem to be just using DC resistance. RF frequency is where impedance really plays a big role in developing circuits. With audio, it's not so much, because you're going to have a high impedance coming off the plate. Typical plate impedance on a vacuum tube is about 100K, and you're dropping it down to less than 1K on both of these. So that's what you're doing. You're bringing that impedance down to a lower level so that the tube can amplify it and do its thing. So I'm going to go ahead and I'm going to install the PT431, which is just the coil, into the iron core of some Chelsea transformers, and I'm going to use those to repair my Chelsea radios. Now the whole purpose of this entire testing was to basically make it so that I feel comfortable with replacing this core with this core. And the reason why is because after unwinding this core, I realized there's no way, absolutely no way, I could wind a core this complex. Now obviously if you put this core in this transformer, it's going to look like dog doo-doo. So we don't want to just do that. There is a way of doing it to make it look aesthetically identical to the original core. Now the way I do that is I take a pill bottle, and that's where I start, and I'm going to cut this pill bottle so that I can basically make a mold that will match this core. And I've already done that. And this is what it looks like when I'm done. Take a little acrylic bar here, and I'm going to slide that onto the bar. But before I do that, I need to get my primary and secondary windings on one side and the other. As you can see, this is on the top and this is on the bottom. I need them both on the bottom. So the way I'm going to do that is I'm going to drill some holes down here. Okay, so what that's going to allow me to do, I'll bring my primary wires over here. My secondary wires, I'm just going to loop them back under, put them down here. And that gets my wires where they need to be. Now I don't need this one, so I'm going to go ahead and snip that one off. It's going to get buried here. Now the way I'm going to hold all these together is with a piece of electrical tape. We'll also cover up that center conductor. So now my wire is oriented correctly. What I'm going to be using to create this form is this stuff called Crafty Clay. It's basically it's a cosplayer type of material that they use to make costumes with. You can make this stuff pretty much permanent by covering it in a varnish or shellac after you're done with it. So all I'm going to do, it's very sticky and gooey. So really all I'm doing is taking this and I'm going to wrap it around this thing, just like this. And I'm going to take my little form that I made. I want the seam to be on the top, so I'm going to go ahead and wrap it around like this, and then I'm just going to press this thing down around it. Okay, once I get that outer form kind of where I want it, I'm going to take some masking tape here. I'll try and close this gap here off. Alright, so as you can see, that's nice and around there. Now the rest of this is just a matter of leveling it off. Now I'm going to go ahead and make up a few of these. Okay, so I've let these set for a couple of hours, and now I'm just going to go ahead and take the form off. As you can see, that's what it looks like. This thing's still very pliable, so I got to be careful. I'm just going to go ahead and let this set up and dry for 48 hours. Okay, so I have these and all these, so I've got a few here to work with. So I don't really need to do this, but I'm going to do it anyway because I want a little bit of protection on these. I'm going to put heat shrink on all 6 of these for the project. So what I've done is I went ahead and taped off the width that I need here, and I scored this all the way around. So now when I peel this off, I can come all the way around it. Alright, there's my finished transformer coil. Ready to go. So here are the 4 different configurations. Here's the table model, which has the base, the top, the side posts that go from the bottom and connect to the terminals on the top. You've got the single bracket, which has a bakelite, one connection in the center here, well, kind of off center here. And then you have the dual transformers here for the Model 130 and the metal version of the Super 5, and that has a single bracket like that goes down the center here to create the 2 connection points. And then you have the one that's used in the Super 5 versions that have the 2 side connectors, which are basically the same bracket, only shorter. And this one here has the spacers. Actually, this one should have it, but these wooden spacers here help to keep these dual transformers from moving around. I got to orient the primary and the secondary. I know the red here is on the primary side. See a little bit of it through the heat shrink. Okay. Okay, come on. Okay. Okay. Alright, so alright. Okay, so here are the final results. I've got these three transformers here. One of them is going into a Model 140. Two of them are going into the ZR30. All three of them I'm working on right now. There's a Chelsea Super 5 that I'm working on, and that's what this pair of transformers is going into. There is a Chelsea Super 5 Deluxe that's going to get this pair of transformers. These two are going into a Bakelite paneled Chelsea Super 5. These two are going into another Bakelite panel Chelsea Super 5. These two are going into the other version of it. These three sets of two are going into ZR4s, and this pair is going into a Model 113 amplifier. And this one here is actually a spare, which I'm sure I'm going to need at some point. Some of these have original Chelsea Model 50 cores that I found were good. Some of these have the PT431s, and some of these just have cores from other transformers that look the same. So now I've got all these and I can start knocking out some of these restorations. So as you can see, there's a lot that goes on behind the scenes on a lot of these restorations. This is just one of the issues that I've had for a while, because I do have a backlog of Chelsea radios, and there's nothing more frustrating than getting to this point in the radio where you have to find a transformer and you just don't have it. So hopefully this will get the ball rolling on getting those things knocked out. This whole process took me a little over a month. A lot of work went into it. It doesn't look like it because of the magic of video, but this is the life of somebody that does a lot of restoration. So it isn't just Transformers. There's a lot of other things that happen behind the scenes that you may or may not see in some of these videos. Well, in this case you did. I hope you enjoyed today's video. Hope to see you again next video. And happy restorations, everybody. Thanks again for watching. Goodbye.